The square root of 2. Why it's irrational. How do we know the square root of 2 isn't rational? Well, to make absolutely sure, here's what we can do. Pretend that the square root of 2 is rational, and then see where that takes us. So let's pretend, just for the sake of argument, that the square root of 2 is rational. Remember, this means that you can write it as p over q, where p and q are both integers, and q isn't 0. So suppose, just suppose, that there is such a p and such a q. This means that if you happen to have an object whose length is the square root of 2, say the diagonal of a 1x1 square, for example, then you can take q copies of this object, line them up end to end, and get the integer p as your total distance. In other words, there's some square with integer length sides whose diagonal is also an integer. In fact, there'd be many such squares. For example, if a square of side length 12 worked, then a square of side length 24 or 48 or 96 would also work. You can imagine that if you were going to build a square like this, it would be a lot of work though, and you wouldn't want to build it bigger than necessary. So, suppose you build this square. The smallest possible square whose sides and diagonal are both integer lengths. You step back to admire your work, but then you wonder idly, is the length of that diagonal even or odd? You happen to know a thing or two about odd and even numbers. For example, if you square an even number, you always get an even number. On the other hand, if you square an odd number, you always get an odd number. So if you square the length of that diagonal, what kind of number do you get? Here's the square in question. Now, what do we know about its area? Well, it's actually twice the area of the square we started with. It's made up of 4 identical triangles versus 2. In other words, we can split this bigger square into 2 pieces, both with integer areas. This shows that the square of the diagonal is an even number, and so the diagonal is an even number as well. Well, that's good to know. Maybe when you see an even number, you just feel like cutting it in half just for kicks. It's just the kind of person you are. You can cut that diagonal in half and cut that big square into 4 little squares with integer side length. It's great. But wait, how long are the diagonals of those little squares? They're the same as the side length of that original square, as it turns out. Well, that's also good to know. But maybe something unsettles you about it. Something seems wrong. And then you realize, these little squares have sides and diagonals that are both integers. That kind of thing wouldn't normally bother you, but you were sure you were using the smallest possible such square to begin with, and these new squares are smaller. They're half the area of the original square, in fact. To make matters worse, you can repeat this process and get even smaller squares, 1/4 of the area of the original, but still with integers for their sides and diagonals. You can break your squares in half again and again, eventually getting squares so small you can't see them, which still should have integer length sides. Perhaps at this point you realize this is all impossible. The integers you know and love don't behave this way. This must be a terrible dream where the laws of arithmetic are broken. So you wake up from your dream, or from your daydream. You're relieved to see that you never really built the square in the first place. But could you build it if you wanted to? It seems like a reasonable thing to do, but whenever you try imagining it, the story always ends the same way, with endlessly splitting triangles and squares, arbitrarily small and arbitrarily numerous, all claiming to represent integers. That way lies madness. The dream begins with a premise that seems reasonable, that the square root of 2 is rational, but it ends with an impossibility, and it can't end any other way. There is an ending to this math fairy tale, though. The way I learned it, at least. When a Greek first discovered this proof, and realized that not all numbers were rational after all, the more mainstream Greek mathematicians were so furious with this departure from orthodoxy that they threw that renegade mathematician off a boat. Or so the story goes. But this act of violence couldn't change the nature of math, or make a complex, maddening, baffling universe into an orderly one. But here's another ending. This same story has happened many times throughout history. When we study the history of math, or science, or maybe any discipline, there are periods when people think we've got it all figured out, that the world is orderly and comprehensible. And then we realize that we were very, very wrong, and that the universe doesn't fit into the box we made for it at all. And whenever that happens, some people get very upset. And they say, The universe is more complicated than we thought it was. This is horrible. And at the same time, other people look at the exact same event and say, oh, the universe is more complicated than we thought it was. This is wonderful.